Alright, what's up, Physics 133? This video is going to show you how to find the electric field at distance h from a line of charge using Gauss's law. So, I learned visually, so I like to start by drawing a picture. Start with our line of charge. Well, here's a line. Let's throw some charge on it. Okay, line of charge. Now, we want to find the E field at a distance h. So let's draw our distance h. How about that far? Sounds good? Alright. The next step is to draw our E field lines. Because it's a line of charge, you'll have E field lines going up, down, coming straight out at us, going down into us, basically creating a cylinder, an infinite cylinder, around the line of charge. For our sake, since we're trying to find the E field at distance h from the line of charge, we're just going to mark our cylinder a distance h, or a radius of h, from the center line. So let's throw some other labels on here, just to make our life easier, because we know we're going to need a few things in the future. One of them being the length of the line. How about a length L? Another thing, as you can read in the problem, it says density with 4 question marks. It probably means density is important. So let's label a density. We have, because it's one dimension, we have our density labeled as lambda. And the units for that are coulombs per meter. So that's our charge density along that line. It'll come in handy in a couple minutes. Okay, so let's move on to Gauss's law. Start by writing down the equation. You have the E field dotted with the Gaussian surface equals the charge enclosed over epsilon, a constant from the front of our book. So, personally, I like to start with the right side. It's just a little easier. The charge enclosed. Well, inside our cylinder, what's our charge? We just have this line of charge here. Length L, density lambda. Well, if we want to get our total charge, all we do is multiply lambda. So you have lambda coulombs per meter times L meters. Using dimensional analysis to get rid of the units, the meters cancel, and you just have lambda L coulombs. Okay, so because epsilon here is a constant, that really finishes off our right side of the equation. So let's move on to the left. For the left side of the equation, we have our magnetic or electric field dotted with the Gaussian surface. So, what's important here when we have a dot product, if you remember, a dot product can also be written as the magnitudes of the two things you're dotting, for our sake, the E field and the Gaussian surface, times the cosine of the angle between them. Back up to our picture. The angle between them is going to be the angle between the E field and the line normal to the Gaussian surface. So let's start drawing some normal lines. For up top, we have normal lines that conveniently are parallel to our E field lines. So you have an E field line and a normal line in the exact same direction. Same goes here, 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 all over the place because it's continuous. The same goes for down below. You have an E field line and a normal that is parallel to it, all around. The sides, on the other hand, you have a normal that goes out in this direction, and an E field line that still goes up, as you can see here, our E field line, which gives you a 90-degree angle between them. That's our theta, right? So breaking this into two parts, because you have two different normal directions, you have an electric field that you need to evaluate here, and an electric field you need to evaluate up here. For us, on this, let's start with the perpendicular side. Plugging this back into the equation, we have a theta of 90 degrees because they're perpendicular to each other. Cosine of 90 degrees equals 0. So, easily for us, all of the Gaussian equation, left side of the Gaussian equation, for the perpendicular side, the kind of edges of this cylinder, are going to cancel. So they're all going to equal 0. So all we have to do is focus on the part where the normals are parallel to the electric field. That's up top, below, coming straight out at us, the whole curved surface of the cylinder. So it kind of turns into a pipe. So let's go back down to our equations. We have the electric field dotted with the Gaussian surface. So let's rewrite that. What is our Gaussian surface? Our Gaussian surface is the outside of this cylinder. We can write that using geometry as 2 pi h, our geometry 2 pi r, but since h is our height, that's also our radius from the center to the top of the cylinder. So you have 2 pi h times L. That gives us our whole surface area along the outside of this cylinder. This is then dotted with the electric field. Now, since this is dotted, all this means is what's the E field in the same direction as the Gaussian surface, the normal to the Gaussian surface? Well, since they're parallel, it's 100% in the same direction. So it's just the E field times 2 pi HL. That's the left side of our equation. So let's throw the right side in now. That, the left side, equals, well, we already calculated our right side up here, as lambda times L. So, equals lambda L. Now it's just math. You're trying to solve for the E field, as the problem asks. Remember, it says, show us how to find the E field, a distance h away. So we're trying to find this E. So let's divide by 2 pi HL on both sides. Now, the right side, sorry, I forgot to put this in, is also divided by epsilon, just from the original equation. Okay, which is just a constant. It's not too hard. Okay, so divided by 2 pi HL. Now we simplify. The L's cancel, and we can write our equation as the E field equals lambda over epsilon times 2 pi h. And there we go. There's our E field found using Gauss's law. Notice that since the L's cancel, the L actually doesn't matter. The E field's going to be the same whether the line's really short or really long. All that matters is that the line goes all the way through your Gaussian surface. So it can go here, here, however long it to be, as long as it's as long as your Gaussian surface. And that's it. Once again, the answer is the E field is lambda over epsilon 2 pi h. Hope this video was helpful, and I will see you guys tomorrow in class. Later.